In this video, we are going to start our focus on IPv6. Now, IPv6 is not widely adopted everywhere in the world yet. It has been around for quite some time, I think right around the turn of the century, 2000, and it's mid-2015 right now. It is not, it's, I think 7% of the internet is IPv6, maybe? I honestly don't know, I haven't looked. But the interesting part about IPv6 is um, how unwell known it is. If you talk to most people in the networking space, at least most people that I've talked to in the networking space, they don't really bother with it. I'm a rare breed. I spend a lot of time in certification and learning technologies and stuff like that. So if you were to take 1,000 people, there might be maybe 10, 15 people like me that would be well versed in IPv6. The rest of the group is probably not gonna. They're probably have heard of it, but not be very well versed in it like I would be, and rightfully so. But what I want to do here is I want to kind of bring you guys from a if you're studying, if you're watching this video, maybe you're watching it just because of the fact that it covers IPv6 from a high level, and we start filtering through the different layers of IPv6 and getting down into the nuts and bolts of how it works. Talk about the addressing, talk about the address types, then get into how it works, the configuration of it, working in a forwarding protocol, and being able to trace route IPv6 and ping IPv6 and get things to work the way we need to, and advertise addresses and stuff like that. Some more complicated designs. We will be talking about OSPF v3, EIGRPv6, and BGP in the address family IPv6. We'll talk about those down the road as they are applicable in most modern networks. But the main thing that I find in most environments is no one runs it. They turn off the IPv6 stack inside of Microsoft, and I don't know if you can do that in Mac. I know you can with in Microsoft and in Windows, both for the server and the desktop platforms. But most people don't run it. And the couple times that I've been called in to work on a v6 network, it's only because of the fact that they're testing. They have a test environment for an application that they want to deploy, or maybe they have offices or sites over in Europe that has just IPv6. So it depends on the situation, but IPv6 I think is kind of shunned, if you ask me, because the fact that it's not well known. It's a very people they see the hexadecimal addressing and they go no, and it's not that bad. I mean, and I'm hoping to demystify it for you, and hopefully by the time we're all said and done, you guys will be like, oh, v6, piece of cake. Because really, when you think about it, v6 isn't very difficult to learn, and I'll show you how to take a look at it and break down how things work, and go from there. So at least that's my view on v6. It's not very difficult at all. So some of the things that I want to recommend to you guys out of the gate, in case you want to know more. Let's say, for instance, you're studying for your CCNP, and if you're like me, the CCNP was my launching pad to CCIE. And as soon as the day that I passed my CCNP, I took my route exam, or I'm sorry, my T-shoot exam in the morning. It was like 9 a.m. I was done an hour and a half later. I came home. I waited all day for the results on Cisco's website. Next thing you know, I check. I get an email from Cisco certification because I completed all 3 exams. I was therefore, CCNP certified, and I got the email from Cisco. I was like, woo! It became a CCNP. I think it was the very tail beginning of 2014, like first week or so of 2014, and from there it was just a matter of going in and getting experience, and then from there on, that's what I've been doing. So. And I've been working CCIE ever since. So I want to recommend a couple of resources for you guys, in case you're not sure as to what to study or how to study. So IPv6 Theory, Protocol, and Practice is a great starting point if you're new to v6 and you want to get familiar with it. Understand the different address types. Maybe you convert hex to decimal, decimal to hex. Actually, I should say hex to binary, binary to hex. Be able to understand what's going on and all the different pieces to it. And ironically, I will be recommending some Microsoft products for you to reference. And the reason for that is whenever you're running v6, you're probably running it in a Windows environment. at least every corporate environment I've worked inside of, you're running Microsoft in it, and v6 is going to be running to some level. Doesn't necessarily mean it's going to be just Microsoft. You might have Linux and Unix running in the background. But at the end of the day, understanding the basics on how it works and how it's going to interact with the TCP/IP stack for v6 and be able to get your applications to be able to talk to v6, those are important. So check out those. For an overview of v6, which if you, like I said, if you ask me, it's not a complicated protocol at all. RFC 2460 is the IPv6 specification. I have read that RFC in great detail. It is chock full of lots of the nuts and bolts. You know, if you really want to rip IPv6 apart and really learn it, that's a great RFC to use that from. And I would recommend reading it. You know, if you are maybe running a v6 environment and you need to know more about it, the details to it, that's a great reference point for you. Now, what's the key difference between v4 and v6? Well, the address space. I mean, it's like v4 has 4.29 billion addresses, where v6 has it actually had to look it up, but it's actually 340 undecillion, which, if you actually were to write that out, it's like 340 with, comma 000, so let's say triple zeros. If you take 10 commas of triple zeros, it's like that big. It's a massive amount of addresses. So it's actually 4 times the address space of v4. Because you're taking 32 bits and you're multiplying that by 4, which gives you 128. So it's a ridiculous amount of addressing. Now, I've debated this with some people. I think it's actually too many addresses. Because realistically speaking, you're not actually solving anything with v6. You're actually just making the problem worse. And what I mean by that is with the global BGP table. Right now, there's about 550,000 routes in the BGP table. Maybe it's pushing 600,000. I haven't checked in a while, but the last time I checked, it was 500,000 routes, 500,000 IPv4 routes. So as time progresses, that number of prefixes will probably start to creep into the 1 million mark, and v6 is that's just like you're not even scratching the surface yet. You haven't even, doesn't even feel when you poke it with the million addresses because of how big of an address space it is. So, but it's a big block, and I think only 3% of it has been allocated, I believe is what the range is, what I've heard, but honestly I don't know. So let's take a look at the addressing format and kind of rip that apart and break that down. So the addressing format is pretty straightforward. With IPv4 dotted decimal, you had d.d.d.d, or decimal, and 1d equaled 1 byte or 8 bits. I'll talk about binary and bits and hex and bits in momentarily. But the idea behind this was you had 1 byte equals 8 bits, and each bit placement had a specific numerical value associated to it. And again, I'll talk about that coming up later. And I'll actually break it down, some addresses, and show you guys how to subnet v6 and v4, kind of combine v4 and v6 in the same addressing in the same video. The IPv6, however, is hexadecimal. Now, IPv6 being hexadecimal, and I'm going to start referring to it as IPv6 and just refer to it as v6. Same thing with v4. So v6 being hex gives it a lot larger, gives it a more addressing bits to turn on and off, more capabilities, larger address space. So for every one of these H's, every 2 H's, okay, you get two H's equals 1 byte. Well, what's half of 1 byte? What's 4 bits equal? Well, 4 bits is a nibble. N-I-B-B-L-E. It's a nibble. So if you were to take the 4 bits here, this H, right? I can't highlight just one. Okay, so that H that I'm highlighting right there, that single H is 4 bits. You take 2 H's, that's 1 byte. That means that this right here each 4 block of H's is 2 bytes. So we have 2 bytes, so it's 32 bits, right? Or sorry, 2 bytes, 16 bits. Apologize. So 16 times 8 is 128. That's going to be your blocking. So you're going to have 16 bytes, or sorry, you're going to have 2 bytes, 16 bits. So you're going to have 4 nibbles per section. So as we go into this, I'm gonna try to correlate how this gets broken down. I'll try to draw it out the best I can in order for you guys to understand exactly how this is broken down. But if you can take what I've got drawn here and then start to expand it out, because this makes it easy to identify it by. Because as human beings, we don't read in binary, we read in dotted decimal and hexadecimal. It's easier for us to identify. So we'll take a look at that as we go along. Now, hex versus binary. What the heck is up with it? Well, binary is a 0 or a 1. It's either on or off. On is 1, off is 0. So it's denoted as 10.1.1.1. So if we were to break this down into binary, this would be, in the first octet, you'd have the bit underneath the 8 would be turned on, and the bit underneath the 2 would be turned on. All the other bits would be turned off. The same thing with 1. The bit under the 1 number would be turned on for the second, third, and fourth octet. So I'll draw this out here momentarily, but that is how it would be drawn out here. So one octet is 8 bits or 1 byte. Each bit has a numerical value assigned to it, and so it's 1 through 8 incremented 1 through 128 incremented by the power of 2. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, so on and so forth. Definitely don't want to be giving you guys a math lesson here. Well, converting would be more like it. And then if you add 128, 64, 32, 16, 8, 4, 2, and 1 all together, you get 255. And that's how, if you have a subnet mask, how you're able to determine how much of the address is network versus host. And I will break that down here momentarily. Now, hex is also binary, 0 or 1, and depending on where it falls into play will determine what you're going to be dealing with. Because of the fact that you have 16 bits, you have a 0 through 15. So the idea here is if you have a 2001 CC1E : 1, see what I did there? CC1E, CCIE. You know, I is not a valid hex character, so I had to flip it over. This right here, if you were to break this down, and I'll explain how this actually looks just to give you guys a heads up for it. So this 2 right here is a nibble. Okay, it's 4 bits. So in that nibble, you're going to have an 8, 4, 2, and a 1. So on the 2, you would turn on the 3rd bit on. So that would be the 2. The 4th bit would be the 1. So you turn the 2 bit on in the first nibble. The second nibble would be all zeros. The second nibble would be all zeros. The fourth nibble would be a 1. So in your first 4 nibbles, or your first 4 bytes, so right here, and these four H's is what this would be constituting as, right? So the first nibble would be 0010. The second nibble would be 0000. The second nibble, or I'm sorry, the third nibble would be 0000, and then the fourth nibble would be 0001. Is everybody tracking with me? And if you don't get this, I'll break it down here just momentarily. When you break this down, so since every H is a 4-bit nibble, you are going to break every H down into 4 bits. So you take every one of these H's and you draw out 4 bits for each one. They can be turned on or off, 0 or 1, depending on the address. And that's how you're able to break down an IPv6 address. Now, it's also important to understand that you can break it down into binary math that way, but what happens if you get a C? What's that C supposed to be? Well, 0 through 9 are going to be your valid characters, or valid integers for binary, for in hex. So 0 through 9, so you're going to have, I'm sorry, we'll take it a step back. You have 8, 4, 2, and 1. So if you add 8, 4, 2, and 1 up, you get 15. So once you hit once you get to a value of 9, by turning on any one of these bits on. So actually it would be 8 and 1. It wouldn't be 4, 2, 1. It wouldn't be 8, 4. It would be 8 and 1. It would give you 9. Once you go 8 and 2, you have then gone from a numerical value to a alpha character. So if gone from 0 through 9, then you've gone to A. So when you add 4, 8, and 2 together, that's 10. So then you're in the alpha characters, which is A through F. So an A is a 10, an 11 is a B, a 12 is a C, a D is a 13, an E is a 14, and a 15 is an F. And I'll break this down coming up here, just so you guys can correlate to it. But as long as you understand the numerical value to the character that is associated to it. So this means that in this group right here, so we have, again, this address would be 0010, all zeros, 0001, right? That would be the first 32 bits, first 16 bits. Now you take this guy, you have 16 more bits. So in this one here, C is going to be would be 13, so that'd be 8, 4, and 1, right? Because that's 13. Because A 13, 10 is A, 11 is B, 12 is C. Oh, sorry, 12. So it'd be 8 and 4. So it'd be 8 and 4. So it'd be 1100, 1100. You have a 1, so it'd be 0001, and then you have an E, which would be 842, and because 14 is 1 less than 15, it would be an E, so it'd be 1110 would be the breakdown for this guy. Does that make sense? I mean, I'm describing this off the top of my head, and I'm breaking it down. I haven't actually shown you guys anything. So now that I've covered that, let me break this down to show you in a more easy to follow point. So I'm going to pull up Paint, and it can be a blank Paint document, so bear with me here. Alright, so what we have, I'm going to grab my pencil here and make it a little bit larger, and I'm going to use red. Alright, so we have, we're going to say the first character we used was 2000, right? 2001 CC1E, and we're going to put the colon there, colon, 1, right? So what we're going to do is, this is 4 bytes, or 4 bits, this is 4 bits, this is 4 bits. Same thing over here, 4, 4, 4, and 4, right? So what I'm going to do is I'm going to break this down like this. I'm going to take these guys right here and break it down like this. Alright, so we have the first guy here is going to be 2001. Or, I'm sorry, it's 2. 2001 broken down into 4 bits. We're going to have is going to be 0, 0, 1, 0, because we have 8, 4, 2, and 1, right? So then we take the second one, and I'm just going to bring this guy out like so. We have 0, which is going to be 8, that's a horrible 8, 8, 4, 2, and 1, which is going to be 0, 0, 0, 0, because it's all zeros. This guy right here is going to be the second 0. Again, 8, 4, 2, and 1, which is going to be 0, 0, 0, 0. Now the 1 here, we're going to break this guy down, is going to be 8, 4, 2, and 1. We're going to type in here 0, 0, 0, 1. So in binary, we have the 2, this is it in binary. The second 0, the first 0 is this, the second 0 is this, and the 1 is that. Now let's break down the CC1E. Okay, and you might be going, okay, that makes sense. And I will break down the conversion for you here momentarily. So, first thing I want to do is bring over the pencil again. So the CC1E. So we're going to do C. We'll draw this out like so. And hopefully that'll make sense. So 8, 4, 2, and 1. So for here, we're going to have a C. So let me actually draw over here on the right hand side the actual hex to decimal, the hex value to the binary equivalent value. I'll pause the video, I'll show you guys how that looks here, and I'll bring you guys back in. Okay, so I have I've created a table there in the lower right hand corner of your screen so you guys can have a reference point. So we have 0 is all zeros in the all the bits here, the bit placement, so 8, 4, 2, and 1. All the bits are turned off, same thing in hex. Now I drew the 0x for a reason. So if you see this particular notation here, the 0x, that's going to be an indication that that's a hexadecimal value for you. So that's going to let you know that it's going to be in hex, and that you're going to have to look at it and try to translate it via hex. That's why I put that in there. So that's going to give you an indication for you there. So now when you're going through, we have the different binary values for it to the decimal value, so the decimal to binary to hex. So I did this off the top of my head, and this is after years of practice. So if you're brand new to this and you don't get it, don't worry, it just takes time. So what I want to do is I want to break down this address because there's hex characters in it. I want to talk about how to break this down to a binary value and how to break it down. So we have our 8421, 8421, 8421, and 8421, right? We have all that situated. Now we want to take that C, and we have to figure out, okay, in the hex, it's a hex character. We want to take a look at the C, so we see the C right here. And then we notice right here that the actual the decimal value for that is 12. So we know that 12 in binary is going to be an 8 and a 4. So that means we need to turn this bit on, this bit off, or I'm sorry, the first two bits on, and the second and third, or third and fourth bits, turn them off. So that's going to be 1100. Same thing here, 1100. Now with 1, we obviously know that a 1 is going to be 0001. Pretty easy to figure that one out. 0001. Now we have the E. We have to go to our reference point and say, okay, it's E is that. It's 14 is the decimal value, and the binary value to that guy is going to be 1110. It's 14. So CC1E is actually 111 or 1100, 1100, 0001, 1110. Okay, is everybody following with me? This is how you're able to convert this stuff back and forth. And this is where it comes handy with how to understand the addressing scheme. Now, I'm not going to talk about how the masking comes into play with IPv6 until later on in the next video. I will talk about IPv4 masking now, because this way here we're going to be taking a look at it from both perspectives and breaking down IPv4 and IPv6 addresses. So that gives you that look on how it actually works. When you're dealing with a local area network or a broadcast segment, you must use a /64 mask inside of IPv6. There's no way of getting around it. I'll talk about the other advancements like EUI64 and doing autoconfig and things like that, and we'll talk about this stuff more in detail as we go along. It's relatively straightforward for the most part, but if you don't understand it or don't know how to get to that, it can be confusing. So we have that covered. So what I'm going to do is I'm going to break down an IPv4 address for you guys to show you exactly how this works. So let me go ahead and wipe all this stuff out, and we'll move into the next section. So, and our next piece right here is we want to break down 10.1.1.2, and we want to break that down to a /24, right? So we want to be able to notate that out with a default gateway of 10.1.1.1. That's what we want to map out. Apologize ahead of time. I am using a mouse to draw this out, so it doesn't look the cleanest, but you get the point. So we want to be able to subnet this out to break down exactly what we're going to be doing. So we want to make sure that we have the right subnet mask for this guy. Well, a class A subnet is going to be a /8 or 255.0.0.0, right? Everybody knows that. If you, and I'm hopefully this is a review, not your first time learning this, because I am moving kind of quickly and I'm not going into a lot of depth. So we have B is going to be a /16, and we have 255.255.0.0. So that is a 5, not an 8. And C is going to be /24, which is going to be 255.255.255.0, right? So those are our subnet mask ranges. So we know that we're going to be using a /24 to map this out. Now, how do you know? Let me actually move this stuff over to the right side of the screen. And let me just move this guy over here so he's out of the way as we're going along here. So let me do this. Let's do a little bit of subnetting for the review for you guys. We want to take, and I'm going to draw out here. We want to, actually I'm going to pause the video for a second, and I'm going to come up with a couple of address spaces so that you guys can't think ahead and cheat on me. Okay, so what I've done is I wanted to hit subnetting from two different angles. We want to take, and we have an allocated by our administrator 10.1.0.0/16. Okay, so we have a lot of address space, and we want to make sure that we can go in and allocate that to all of our regional offices. For the regional office admin, we would need to break this down. We need 8/23s. So we need to figure out, based off of that, how many different networks do we need to, we know how many subnets that's going to be. We need to figure out the binary association to the subnet mask to figure out how to associate that, and then what the ranges are going to be for each subnet. And then our second one we're going to take a look at is we've been given, we have allocated a /24 for one of our sites, and we're not worried about overlap. So I'm going to point that out right away. I don't really care. I just want to make sure you guys understand the idea. You're given a /24 and you have an 80 user subnet, a 45 user subnet, so it's 125 users, another 35 subnet user, so it's going to be 160, a 14, so it's 174, and then 2 point-to-point links. So you need to be able to take this single /24 block and break it down into multiple or longer matches. So the first one we're going to do is actually relatively easy. The first thing we're going to take a look at is we know that a /23 is going to be our subnet mask. So that's already given. This is how you kind of reverse engineer a subnet. So you know what the mask is already going to be. You don't have to guess the mask. So based off of that, you know that you're going to have to figure out, okay, what is the total? What does the /23 represent in what's the word I'm looking for? In accordance to the total users for that subnet capability. So how many users does that subnet mask hold? Is basically what I'm trying to say. So we know that a /24 is what? How many users? I'm going to get very specific. It's 252. You can't use the base subnet, so that eliminates one address. You can't use the broadcast address because that's the broadcast, and you can't use the default gateway. So that takes 3 addresses off the top, so that gives you 252 usable addresses to go. So 255, 254, and 253 are all gone. So you have to use 252 through 254. Those are the ranges you can use. So what we're going to do, we're going to take a look at this and figure out exactly where we're going to be going with it. So we have a /23. A /23 is 255.255.254.0. Okay, we know our mask. Now, if I was to take that in accordance and say, okay, I know what that breaks down to, but I need to figure out from a well-known spot. So a well-known spot is going to be a /24. So /24 is going to have 255 users. We're just going to go with that round number. So if we know that, if we were to take that down a bit and go to /23, a /23 is going to be double that. Technically, this 250 is actually 256, but I'm not going to argue the mediocrity and the can't think of the word that I want to use, but we're going to go with 255 because it's a round number. So a /23 is going to be how many users? We're going to say 1024. 1024. Was that right? No, it's not. 256 or 512. So 512 users for that subnet. Now, what you need to do from here now is once you have this piece figured out, you know that that's going to be 2 ranges, right? Or at least I would hope you would know that. So 256 times 2 is going to be 512. So you have that. Now you know you're going to have 2 blocks. So where do you start? And yes, IP subnet 0 is applicable here. So where would you start? I would start at the base subnet. Start from the top, or start from the lowest address and work your way up. That's what I always do. Now, when it comes to supernetting, when you're taking a single subnet and you're breaking it down into longer matches, you always start with the bigger number first and work your way down to a little number. But we'll talk about that coming up here momentarily. So that means based off of this subnet mask, we're going to have approximately, we're going to have a 10.1.1.0 through a 2.0/23. Because when you have a /23, you're taking two /24s and you're advertising it as a single /23. So you're advertising two /24, so you're advertising 256 host networks, which you're saying I'm advertising one 512 host network. So 10.1.0 through 2.0/23. Then you're going to 10.1.3.0 through 4.0/23. And then you're going to continue down the 4.0, sorry. And then you continue down the pace until you get all the way through your 8 subnets. So right now we have 2, 4, we need 4 more. So 10.1.5.0 through 4 or 5.0, 6.0, 6.0/23. Okay, that's going to be that one. And then we have 10.1.7.0 through 8.0/23. That gives us our, and we need 8/23s. So we have 4 so far. So I miscounted. So then we have 10.1.9.0 through 10.0/23. That gives us our 5th. And 10.1.11.0 through 12.0/23. And again, it just repeats itself. So you just keep adding up. You skip 2, and that's what it's going to be broken down to. I'm putting that through 2 so you guys get that. You're taking 2 blocks of /24s, making a single /23, and then sending it out the door. That's how that would work. So that's how you would go about figuring out supernets. That's how you would do that. It's actually pretty easy when you think about it, but actually what I'm just going to do is I'm going to blow this guy away. It's quicker this way. Because I was born that way. I was subjected to Lady Gaga the other day. Yeah, that wasn't very fun for me. I'm a rock fan, so Lady Gaga was not my ideal choice of music. So now, for those of you that are, there was a question. So reverse engineering a subnet is taking what you already know subnet mask wise, finding the bit in the range, and then reassociating. I guess you could look at it that way. Basically, what I would do is if I was trying to reverse engineer, and this is off the top of my head. I know I've done this so many times and I've studied it so much that it's second nature to me. But basically, the easiest way and the quickest way for you guys to look at it would be if you have finding the bit range, finding out what it's associated to, and then knowing that a 512 host is equal to a /23. That gives you your associations. But you have to know this ahead of time to get there. So that's why I'm not going super duper deep on this, because we're not CCNA here. We're CCNP. So now what I'm going to do is I'm going to break down this guy, and we're going to go from there. And subnetting in IPv6 is kind of sort of the same. I'm not going to cover that here. I think that's out of scope for the exam. But just knowing how it works is more important. So anyway, we have a 10.1.0/24. Right, so now we need to break this down into different groups of users. So what I'm going to do is I'm going to set up an 80. I'm going to come down here. I'm going to do a 45. I'm going to do a 35. I'm going to do a 14. And I'm going to do a 2. Alright, so what I'm going to do here is I'm actually going to draw this out. I'm going to type in 128, 64, 32, 16, 8, 4, 2, 1. I'm going to drag this guy over just a bit. And I'm going to go home, copy and paste this, go down here, and I'll actually take that back. That's better. Whoop. hit the enter key there. Now what I did here is I want to add this in so that you guys can see what this looks like. Alright, so here's what we're going to do. We're going to break this down and figure out what our bit length is going to be. This is to find the subnet mask, okay, so that we can associate this accordingly. So the idea here is we need to figure out based off of the host address. So let me flip over to black here. So we know how many hosts we're going to have on a subnet. So that's going to dictate from there how we're going to associate our subnet mask. Now, the way you do this, and it's actually very, very simple. You figure out what your host quantity is, and you try to find a binary value that is equal to or less than that value. So, what number is 80 smaller than in this list of numbers? Well, you guys are going, duh, 128, so I would go correct. So 128. And then all these other guys are zeros, right? I'm going to go across the line, they're all zeros. Now, what is a 128 equal to as a subnet mask? Well, I'm going to draw it out real quick up here. Grab the text thing here. We're going to do a, we'll type 128, 64, 32, 16, 8, 4, 2, and 1. Draw this across real quick, just so you guys are associated to it. We're going to have a, and remember that let's tab this over here and go home and type in 256 is a /24. We're just going to do 120. We're doing 256 simply for the fact that it's 128 times 2. So we're going to have a /24, /23, /20. I'm sorry, /25, /26, /27, /28, /29, /30, /31, /32. Okay, so now we have that broken down. If we take this again here, and we know that a 1 bit, so we've got this bit turned on right here, it's going to be a /25, which is also going to mean that we're going to be turning on the bit in the 4th octet, which means it's going to be that this guy is going to be .128, right? And it's, for the sake of argument, they're all 255. To start out with, 255.255.0. This number right here, this guy right there, that 0 will change per octet as we go through. So right now it's .128 for this one. Now 45, what number is greater than 45 that we would need to allocate? So 32 is obviously too small. We can't. We have 2 subnets of 32. So 64 is where we would do this. So we're going to put in 1, 1 here, right? All these guys would be 0. So this means 128 and 64 is what? 192. So that means that 192 is going to be .192, 192, which is also going to associate us to. So this guy right here is going to be a /25. This guy's going to be a /26. Now 35. What is that equal to? Well, that is also bigger than 32, so we're going to have a second one here. And you might say, well, you ran out of address space, and actually you're right. So we're going to say this is a 30 for the sake of argument. I didn't do a very good job of blocking that out. So we have a /30. Or I'm sorry, we have 30 hosts. So we have 32. As would be the lowest number, because that's actually what I was going to do. I was going to go 128, 64, 32, 16, 8, so on and so forth. So we have 30 hosts. 32 is the number that doesn't go above it. So that means it's going to be dot. So if you take these numbers right here, so 128, 64, 32 is 227. Or sorry, 224. So 224 equals a /27. So we have that. So that's going to be where we go with that one. 14 is going to fall under the 16. So it's going to be 1, 1, 1, 1, 0 all the way across. So it's going to be .240 or a /28. And then we come down here to 2. So we have a handful of addresses left. So we have, we'll say we have 2 point-to-points. So that means it's going to be 1, 1, 1, 1, 1, 1, 1, 0. So it's going to be a 252 or /30. Okay, that's how that breaks down. So that means that the subnet mask for each one of these guys is going to be, and I'm going to speed this process up a little bit, .128, and I'm going to take this guy here and go across, copy this, and this guy's going to be a .192, this guy will be a 224, this guy will be a 240, and this guy will be a 252. That's how the subnet masks are going to be broken down. We've basically taken a /24 and distributed it across 5 different subnets, well actually 6 subnets, and we've allocated it. We haven't gone over 254 addresses. So that's basically how this would work. So V6 works in a lot of the same ways. Again, I'm not going to cover that. I just wanted to break down, do some subnetting, and talk about IP addressing and talk about how that would break down. You can do this, if you can break this down pretty equally, then you're in good shape for the most part. You won't have any problems. So that's how you're able to break down things and go along. So that's pretty much what I wanted to cover here. We're going to talk about IPv6 address types in the next video and break down exactly which one does what and how to allocate things and what they do. I hope this has been informative for you, and I'd like to thank you for viewing.